Let's go ahead and begin. Thalidomide. In the early 60s, a rash of birth defects occurred among women who were known to have taken thalidomide. Thalidomide was a very common sleep drug given to pregnant women. At the time, they didn't find anything wrong when doing animal tests, and it put pregnant women to sleep with no apparent ill effects. However, it turns out that thalidomide would cause pregnant women to be given birth to deformed children, as you can see in the picture. Pretty sad. So, organic and biochemistry was employed to figure out how was it that thalidomide was causing people to give birth to children with no arms and legs. So on a side note, organic chemistry is anything where we study carbon. I know you've heard the term organic all the time, but in chemistry land, whenever we use the term organic, it refers to any molecules that have carbon in it. So here's a nice example right here. In this molecule, using the ISIS draw, we can see a molecule. This is an example of an organic molecule because it clearly contains carbon. Now, biomolecules from biochemistry are any molecules that are associated with life. So they don't necessarily have to have carbon in them as long as they somehow relate to life. Using the term molecule very loosely, one of the best examples is salt. Salt is a key ingredient in life, NaCl. However, it's not considered an organic molecule because there's no carbon present. Here's an example which I think is pretty cool. Sugar. Sugar is found in life. It powers life, so to speak. So, showing off my example. Sugar has the chemical formula C6H12O6. So, sugar is an organic molecule because it contains carbon. That's my attempt to draw an arrow and it didn't work out too well. Let me see if I can use a highlighter. There we go. So, I'm going to go ahead and highlight the carbon, C for carbon. So sugar is an organic molecule because it contains carbon. Sugar is also a biomolecule found in biochemistry because it's associated with life. I think I've beat that to death. Let's move on. So using organic and biochemistry, we learned that once we were able to figure out what the structure is, if you notice highlighted in the slide, we found that thalidomide was actually a twin. So think of your hands as being mirror image twins of each other. The fancy word is enantiomers. I'm not going to test you on the word enantiomers, at least not yet, but I wanted to point out to you that using organic and biochemistry, we were able to figure out that there was a good twin and a bad twin. The good twin is R-thalidomide. The bad twin is S-thalidomide. That's the notation R and S for figuring out twin types. We'll worry about that at a later point. Bottom line is, just by this location of this one single hydrogen, that hydrogen being on a different part of the molecule. One is on the top, right here. One is on the bottom, right here. That determined what type of chemical reactions occurred in the body. If we had our thalidomide in the body, then you would be put to sleep. If you had S-thalidomide, then S-thalidomide would actually inhibit the growth of new blood vessels, such as in the limbs of growing babies, and babies would be born without arms and legs. Pretty sad. But organic and biochemistry was used to crack this dilemma. Interesting enough, they now have revamped thalidomide, and they now give it to cancer patients, because it turns out that thalidomide inhibits the blood growth of new cancer clusters or cancer cells within the body. So let's move on. At this point, the course is broken up into two parts, organic and biochemistry. We're going to study the first part, organic part, and then we're going to study the biochemistry part. In organic, we learn how to speak organic chemistry, methane, propane, 2-methyl-butanol, and we learn key organic reactions. In biochemistry, we learn about popular biomolecules found in the body, such as sugars and proteins, and how they work in the body, which we call metabolism. So in the first part, we focused nothing but on organic. I do want to point out that this is a chemistry course for health majors. Basically, we smashed down 2 years of organic and biochemistry into a half semester. So basically, we're taking the highlights. Sometimes I go into detail, for example. Other times I do not, because we have so much information to cover. If you have questions on a particular topic and would like to learn more, feel free to email me. Now, focusing on organic chemistry, we have several names for different types of organic molecules. The first name is hydrocarbon. Hydrocarbon. So let me change colors just because red's getting boring. How about green? The hydro part, what I'm highlighting here, refers to hydrogen, and the carbon refers to, go figure, carbon. So, common examples of hydrocarbons are natural gas, which is methane, ethane, propane, butane, all of the gases that we love to combust. Crude petroleum, those are also hydrocarbons, and so forth. So hydrocarbons is another specific word for organic chemistry molecules. I want to point out for organic chemistry, we tend to focus on only covalent bonds. So in this slide right here, I'm going to go ahead and highlight, if you can see that, the word covalent bond. Consequently, whenever we're dealing with a covalent bond, we like to use dashes. Dashes. Like to use dashes between the hydrogen and carbon, and that represents a covalent bond, which is a sharing of the covalent electrons. In inorganic chemistry, such as studying salt, for example, they use ionic, but we're not going to focus on that. It turns out that covalent bonds, using Vesper theory, the pairs of electrons in a covalent bond repulse other pairs of electron in a covalent bond. So these repulse each other, R-E-P-U-L-S-E. What this means in a more practical perspective is that it creates these nice spread out bonds. So in this case, here's an example of methane, and because these pairs of electrons repulse each other, the atoms that are connected are spread out. Consequently, they create these nice three-dimensional shapes. So in this case, for methane, it creates a tetrahedral structure shape. Nature loves using organic molecules because as we add together more and more carbons, they create more and more exotic shapes. And it turns out that on a molecular level, every unique shape has a unique chemical property or physical property. So just by changing the shape of a molecule, we can change its properties. And so there are endless structures and endless properties thanks to carbon. I want to point out that for every carbon, we're going to obey the 4-bond rule. Every carbon will always have 4 bonds. So highlighting this molecule up here, if you can see me highlighting it, every one of those carbons has 4 bonds. Notice how I'm focusing on organic chemistry. The other type is inorganic, where there are no carbon present, such as potassium sulfate, and let's avoid inorganic. Here is a general table you have to know. Hydrocarbons, we just talked about that. Carbons and hydrogen are present in a hydrocarbon. And hydrocarbon derivatives. Now, if hydrocarbons contain nothing but carbon and hydrogen, hydrocarbon derivatives contain carbon, hydrogen, and any other element. I'm just going to call this X. And X will be for any other element. So, focusing on this part right here. Again, carbon contains carbon and hydrogen. So methane is an example, CH4 of hydrocarbon. Hydrocarbon derivative is carbon and hydrogen and any other element. So in this case, fluorine is another element, so methane fluoride. So taking this concept really quickly, let's go to my viewer. What would this be? This would be a hydrocarbon or hydrocarbon derivative. This is a hydrocarbon. A hydrocarbon. So, hydrocarbon. Now, if I wanted to, I could modify this and turn this into a hydrocarbon derivative simply by adding in another element. So let me change all of that. So I got rid of a methyl group, carbon, 3 hydrogens, and I added in fluorine. So this is now a hydrocarbon derivative. Okay, so let's move on.